In this video, we will prove some properties that vector spaces have. Recall that one of the requirements for a mathematical structure to be a vector space is that it had to possess an identity for vector addition. And our first theorem says that this identity is unique. So let's suppose that there is an element u of the vector space V, such that u plus v is equal to v is equal to v plus u for every other element v of the vector space. And what we are going to show is that u is indeed the additive identity which we denoted by 0. Okay, but this is easy because u is equal to 0 plus u, since 0 is the additive identity. And 0 plus u is equal to 0 because we assume that u is the additive identity. So this means that u is equal to 0, and indeed the identity for vector addition is unique. Our next result says that inverses for vector addition are also unique. So let V be an element of the vector space, and suppose that u and u prime are both additive inverses of V. And what we want to show is that u is equal to u prime. Okay, so let's consider this expression. We consider u plus v plus u prime. Now, since we assume that u prime is the additive inverse of v, this means that v plus u prime is equal to 0. And so u plus v plus u prime is equal to u plus 0, which is equal to u. But now, let's begin again with u plus v plus u prime, and let's use the associative property to write it as u plus v plus u prime. But since we also assume that u is an additive inverse of v, then this is equal to 0 plus u prime, which is equal to u prime. So indeed, we have shown that u is equal to u prime, and so the additive inverses are indeed unique. Our next result says that vector addition is left cancellative. What this means is the following. If we are given u, v, and w, elements of the vector space, and we are told that u plus v is equal to u plus w, then we can cancel the u, which appears at the left of both expressions, and get that v is equal to w. Let's see a proof of that. And let's begin by writing u prime for the additive inverse of u. Then u prime plus u plus v, by the associative property, is u prime plus u plus v. But u prime plus u is equal to 0, since u prime is the additive inverse. So this is equal to 0 plus v, which is equal to v. But exactly the same argument shows that, okay, so we start with u prime plus u plus v, and we know that u plus v is equal to u plus w. And exactly the same argument shows that this expression is equal to w. So indeed, v is equal to w. And in fact, a similar proof shows that vector addition is also right cancellative, meaning that if v plus u is equal to w plus u, then v is equal to w. This can be shown either by a similar proof as above, or in fact, we could use the commutative property of vector addition. Because if we know that v plus u is equal to w plus u, then we know that u plus v is equal to u plus w. And since we know it's left cancellative, we get that v is equal to w. Our next result says that for every element v of the vector space, 0 times v is equal to 0. But we need to be a little bit more careful. So the first 0 appearing is a scalar, so it's the 0 of the field. And this 0 here is the 0 of the vector space. So we've been here more explicit in order to distinguish between the 0 of the field and the 0 of the vector space. And to prove this, we'll start by writing, okay, so we have the expression 0 times v, and we write the 0 of the field as 0 plus 0. And now we'll use the distributive property to get that 0 plus 0 times v is equal to 0 times v plus 0 times v. So now we have shown that 0 times v is equal to 0 times v plus 0 times v. And we're going to deduce from this that 0 times v must be equal to the 0 element. But we do know, because the 0 element of the vector space is the identity of vector addition, we do know that 0 times v plus 0 is equal to 0 times v, which, as we have shown above, is equal to 0 times v plus 0 times v. But now we know that vector addition is left cancellative, so by cancelling this part and this part, we get that 0 is indeed equal to 0 times v. And this is what was required. Our next result says that if we are given any element of the vector space, any element v, then minus 1 times v is equal to minus v, whereby minus v we denote the inverse of v for vector addition. Okay, so it's enough actually to show that v plus minus 1 times v is equal to 0, because then the result will again follow by the cancellative property, because we also know that v plus minus v is equal to 0. And what do we have? We start with v plus minus 1 times v. And in order to prepare it, in order to use the distributive property, we write v in the form 1 times v. So this is equal to 1 times v plus minus 1 times v. By the distributive property, this is 1 plus minus 1 times v. So this is equal to 0 times v, which by our last result is equal to 0. And here we haven't been so explicit, but this 0 here is the 0 of the field, and this 0 here is the 0 of the vector space. And our final result says that if we take any scalar lambda in the field, then lambda times the 0 vector is equal to the 0 vector. To prove this, let's start with lambda times 0. This is equal to lambda times 0 plus 0, since 0 is the additive identity. By the distributive property, this is lambda times 0 plus lambda times 0. And now, because we also know that lambda times 0 plus 0 is equal to lambda times 0, we have that lambda times 0 plus lambda times 0 is equal, which appears here, is equal to lambda times 0, which is equal to lambda times 0 plus 0. But now by the cancellative property, we do have that lambda times 0 is equal to 0, which is what was claimed.